Also, my presentation is about answer counting in the context of ontology-mediated queries. And it's joint work with Cristina Feier and with Marcin Przybylko. David already mentioned that. Let me start with making precise the problem that we consider. And this is a very basic problem. It's just counting the number of normal, ordinary, certain answers to an ontology-mediated query. So more precisely, we're given as input an A box and an ontology-mediated query, and then we just want to compute the cardinality of the answer set. So this is different from what was done in the previous presentations. We don't have any special counting mechanisms in the query. There are no counting variables. There are no counting queries. Also, we do not distinguish between different models of our knowledge base. We only want to know how many answers are there. Why is this interesting or could be interesting? Well, one reason is that, of course, there can be many answers. There can be exponentially many answers in the arity of your query. And before you try to compute all of them, you might want to be informed that there are very many. And then there are applications where you are really more interested in the count rather than in the actual answers, in particular in data analytics and in decision support. And also counting the number of answers is something very essential in databases. It's supported by essentially every database management system out there. Okay, so in our case, ontologies will be sets of guarded TGDs or guarded existential rules, if you prefer that. But our results also apply to Horn description logics, in particular to ELIH. I will not make that explicit in the remainder of the presentation, but if you prefer description logics over existential rules, you could hear ELIH whenever I say guarded TGDs. The results are all valid. Now, what we are most interested in here is when can answer counting be done efficiently? And to answer this question, of course, we first need to decide what we mean by efficiently. And we equate that here with fixed parameter tractability, where the parameter is the size of the ontology-mediated query. So in other words, let me spell that out a bit, what it means. It means what we want to achieve for computing the number of answers is a runtime of this form here. So f is an arbitrary function. As long as it's computable, we don't care about the growth rate, and we want to be polynomial in A. Yeah? So you can think of this as decoupling the expensive computation, which is this and involves the ontology, from the computation that involves the part of the input which is large. Yeah? This is the A box, and in the A box we're only polynomial. Okay, as a starting point, let me tell you what is known about answer verification. So not counting, but verification. What do I mean by that? I mean the problems that we usually study for ontology-mediated queries. Given an answer candidate, please decide whether this really is a certain answer or not. In a POTS paper this year, that we have published together with Pablo Barcelo and Victor Dalmau and Andreas Pires, we have clarified the frontier of FPT for answer verification. And the results as follows. If you take a recursively enumerable class of ontology-mediated queries, where the ontology is a set of guarded TGDs and the queries are UCQs, then you can do answer verification in FPT if and only if the tree width of the OMQs in your class is bounded by a constant modulo equivalence. Or to spell it out a little bit more precisely, there is a constant k such that every ontology-mediated query in your class is equivalent to an ontology-mediated query of tree width at most k. Now, let me explain a little bit further. What do I mean by this? Well, when I speak about the tree width of an ontology-mediated query, I mean the tree width of the actual query in it, more precisely of its Geifmann graph, because we have predicates of higher arity here, right? And even more precisely, only of the existential variables. So before we consider the Geifmann graph, we drop all the answer variables, and then we look at the tree width. And this is what characterizes for verification the frontier of FPT. I should also mention two other assumptions that are made here for this theorem. First is complexity theoretic, that FPT is not the same as W1. I would not worry about that. That's a standard assumption from parameterized complexity theory. And the second is that the relation of all the, the arity of all the relations that we use is bounded by a constant. That is a more serious restriction. I cannot discuss it further at this point, but I will make the same assumptions in what we do now on counting. Okay, if you view these results on verification as a starting point, also for understanding counting, then the natural first question is, how are verification and counting actually related? And well, there's one thing that is easy and obvious. If you take Boolean queries, then verification and counting are, of course, the same problem. Yeah, a count of 1 means true, a count of 0 means false. But this is not the case for queries that have answer variables. In particular, there are classes of queries that are easy to verify but hard to count. Let me show you two such classes, and this is only conjunctive queries. There are no ontologies here. So the first class is this. The queries take the form of cliques. All variables here of increasing size. Yeah? All variables here are answer variables. And if you look at this class of queries, then verification is trivially in p-time, because what do you have to do? You get an answer candidate, right? The only thing you have to do is you have to verify that all the edges are there in your answer candidate. Yeah? That's easily possible in p-time. But while counting means now, that's the parameterized problem of counting all cliques in a graph, yeah, where the parameter is a click size. And this is a problem that is sharp W1 hard. So sharp W1 is a counting parameterized complexity class, and therefore most likely not in p-time and not even in FPT. The second class of queries that I would like to mention are star queries. To understand why I call them star queries, let's look maybe at this query here. There it's most obvious. So what is this? Well, we have at the center of the star, we have a variable which is a quantified variable now. And at the end of all these rays here, we have answer variables. And as you go along through this class of queries, the number of answer variables will increase. Then it's again not super hard to see that verification is possible in polynomial time. But counting is even harder now. It's sharp W2 hard. Yeah? Okay. So what does it mean? We have seen that TreeWiz is the right way to characterize FPT for verification. Yeah? But verification and counting are different. So obviously we need some other characterization for counting. What is that? Well, we use several structural measures. First, we do use TreeWiz, but a slightly different version of TreeWiz, in which the answer variables also contribute. Yeah, remember that we had dropped the answer variables. They do not contribute to TreeWiz for verification. Here, they do contribute. That's the first thing. The second thing is another measure that is called contract TreeWiz, and I only want to explain it to you using an example. Take this conjunctive query here, where again the filled circles are answer variables and the hollow circles are quantified variables. Then we first manipulate our query, and we manipulate it by dropping quantified variables. Let's start with this one here. But we don't just drop them, we compensate by adding extra edges between answer variables. So in particular here, there was a pass from this answer variable via the quantified variable to this answer variable. We compensate by putting an edge. Actually, you find more such paths. We need to put more edges to compensate. And then we also drop this quantified variable, and again, we compensate. Yeah, and we have a new query, and now we look at the TreeWiz of this new query, and that's the contract TreeWiz of the original query. Second measure, yeah, TreeWiz, contract TreeWiz. There are two more. One is called star size, the other is called linked matching number. I cannot define them in full detail. Let me only mention that the class of queries that you had seen on the previous slide, yeah, these star queries, this is a paradigmatic examples of a class of queries that has unbounded star size. Star size gets bigger and bigger and bigger as you increase the number of rays in these stars. Okay, now I am in the position to show you our main result. So it goes as follows. take any class of ontology-mediated queries where the ontology is a set of guarded TGDs, the actual queries are UCQs, and they're all based on the full AWOC signature. We don't have results when the AWOC signature is not full. Then there's a class of conjunctive queries. I will not tell you at this point what exactly it is, but this class of conjunctive queries, the structural measures of it determine the complexity of answer counting of the class of ontology-mediated queries that we started with. So in particular, if the treewidth and the contract treewidth of this class of conjunctive queries is bounded, then the ontology-mediated queries that we started with can be evaluated in FPT. If the treewidth is unbounded, and the contract treewidth is bounded, your W1 equivalent. If the contract treewidth is unbounded and the star size is bounded, your sharp W1 equivalent. Sharp W2 equivalence is linked to unbounded star size and bounded link matching number, and unbounded link matching number means sharp A2 equivalence. So let me say a few words about what you see here. So the frontier between FPT and hardness, right, is between the first point and all other points. So bounded treewidth and bounded contract treewidth, that's what gives you efficiency of answer counting. I should also note that when you might not be familiar with all these complexity classes, but as you walk through them from the top to the bottom, yeah, they only get increasingly harder and larger, the classes. And last, it is not very hard to verify that this characterization here is exhaustive. So one of these 5 cases must always apply, meaning that these 5 complexities here are the only ones that can ever occur. Now, I should mention, of course, that we did not come up with all these measures. Neither did we come up with a pairing between the measures and the complexity classes. Yeah? We use a very nice result that has been developed over the last maybe 10 years or so in a series of papers, starting with Dalmau and Johnson, and then Durand and Mengel, then Chen and Mengel, and then Holger Dell and collaborators, that has resulted in an equivalent characterization for conjunctive queries and for unions of conjunctive queries. And we add ontologies, guarded TGDs on top. Okay. I haven't yet told you anything about this class of conjunctive queries whose syntactic structural measures tell you something about the complexity of the ontology-mediated queries. Let me try to quickly walk through this. I don't have a lot of time. So here's how we construct this class. Yeah? We start with our class of ontology-mediated queries. And the first thing that we do is we eliminate the existential quantifiers in the rule heads of the ontology in an equivalence preserving way. After that, we take the conjunctive queries out from the ontology-mediated queries. Actually, they have UCQs inside because of the writing, so we take the conjunctive queries out of that. And then we combine them conjunctively in a certain way, guided by the inclusion-exclusion principle. That's important when you count UCQs. Inclusion-exclusion plays an important role there. Then we chase the queries with the ontology, which is finite because we have written away the existential quantifiers. And then we take the homomorphism core. And all conjunctive queries that we can construct in that way, this is what constitutes our class of queries that we then use in the theorem that I had shown. Okay, I think my time is basically over. If you define your class of conjunctive queries in this way, showing the upper bounds is not very difficult, essentially because after having written away the existential quantifiers, you can chase finitely. The lower bounds, we reuse a lot of techniques from Chen and Mengel there. These are very nice and powerful. Of course, we have to add something on top because we need to deal with the ontology. And at one point, we show the slightly surprising thing that you can actually remove the ontology from the query and at the same time make the query self-join free, and the complexity of counting stays the same. There are some more results that I don't want to go through now. I will just put them on, and then I'm ready to take questions if there are any.